So my name is Matthew Kirk. I'm an associate professor in geology, and I'm going to talk to you guys about how geology influences the world around us. And I'll focus on some examples from human populations, but it ripples down beyond, much farther beyond that. And I'll kind of close with that at the end. But as requested, I'll tell you a little bit about myself. So I am a faculty member in the geology department, and my research is mostly focused on active processes, so the modern world, not the deep geologic past. I study the chemistry and microbiology, mostly of groundwater, but also soils and streams to better understand things related to water quality and carbon cycling. So here's an example of a stream bed where there's groundwater discharge and some iron oxidation occurring. And those are microbial processes that are, causing these redox reactions to happen that have a pretty big impact on the composition of the water. And it's just a vivid display of that because you've got these beautiful iron oxides forming along there, basically rust, right? So my research is best described as like geochemistry or geomicrobiology. And sometimes when people ask me rock questions, I tell them, well, I'm not that kind of geologist, but I do know some stuff. So, enough to I think get us by here today. And don't hesitate to ask questions at any point as we go along. And I should mention also, beyond being, as a scientist, we're also people. I'm a father with 2 young children, and my wife also works here at K-State. And so we've just been kind of running around dealing with uncooperative toddler this morning. And so that's why I'm late. And I'm, again, really sorry about that. And I hope that hasn't caused an inconvenience for you all. All right, so today I want to talk about, I've kind of divided this up into 3 parts. I'm going to talk about a fertile crescent in the deep red south, and then highway of grass here in Kansas, and then a big pile of silty sand over in western Kansas. So I'm going to, as I said at the very beginning on the title slide, I want to kind of illustrate how geology influences life, focusing on human society. And I'm starting with an example that's outside of Kansas because it's a really vivid example of what I'm trying to convey. So it's a fun example, one of my favorite examples of this topic. So this is a map that shows the results of the 2008 presidential election. And you can see one of the things that really stands out is this strip of blue down here in the south. And it wasn't unique to 2008. It's you can see it in 2000, 2004, and I suspect you can still see it in subsequent elections, but I haven't confirmed that. So it might seem unusual. It's not usually what we think about when we think about the South and the political landscape, but this strip of blue right here ultimately can be related back to things happening about 100 million years ago. So about 100 million years ago was the Cretaceous period. So before I go further, let me just say, I'm going to be throwing some terms out there, geological terms. If at any point you want me to stop and kind of explain a little bit, some background before I move forward, please let me know. I don't know too much about the background of everybody involved, but I've seen the PDF that you've been given. And so I think you have some familiarity with things like the geological time scale and like the Cretaceous period. But again, if you want me to talk about that in more detail at any point, just let me know.
Hey, Matt, I can tell you that they all have a geological timescale laminated sheet in their information so they can get it out, and you can use all the terms you want. Go for it.
Okay, thank you. That helps. So during the Cretaceous, this is a map of this paleogeographic map of North America. We can see that there was this shallow inland sea. Of course, we have some really nice Cretaceous rocks that were deposited in Kansas during that time. Some beautiful fish fossils, some really cool stuff. But down here in the area that we're looking, there was this coastal plain right there in the south. So I'm going to go back, and you can see where that region is in the political map. And it lines the coastal area right down here, about 100 million years ago during the Cretaceous period. And it was really fertile, a really fertile area in the ocean. There was much higher CO2 content in the atmosphere then, which can help stimulate biological primary production. So these were phototrophic organisms living in the ocean, and they generated a bunch of biomass that falls down. And you see this happening in coastal areas today because of nutrients coming into the ocean. You accumulate a bunch of these plankton biomass, a bunch of plankton biomass in the ocean sediments. Eventually, those sediments became rocks, and it's Cretaceous age rocks, and you can see this strip of them in that part of the south. It turns out that the soil that was formed from those Cretaceous rocks that were rich in plankton was extremely productive. It was very fertile, and it allowed much greater production of cotton in that region, and it's a relatively narrow strip. And I think they actually called it the Black Belt, not referring to the demographics, but because the soil was very dark, rich, like extremely fertile soil. So really high levels of cotton production in that area. And so as a result, if you're making more cotton, and this is antebellum South, they needed more people to help produce that cotton. So there were more hired, much larger plantations and hired. And then of course today that expresses itself as higher density of African Americans still today in that region. And because the proportions of those folks that vote for Democratic presidential candidates, you can see it expressing itself on that political map. So standing back, we put this all together, we see that because the coastline was there, because it was very productive, that led to a very productive soil in that region, which affected how humans were using the land, and how many slaves they had. And ultimately that is affecting the demographics that exist there to this day. And ultimately, how those counties and precincts are voting. So it's pretty interesting to see how this ripples through time, and ultimately it comes back to the geologic processes that were happening long before humans. Vivid example of geological influence on humans today. But let's look at a couple right here in Kansas. And I think most people are going to be pretty familiar with this first example that I have here. Now we have this long history of grazing in the Flint Hills, and it reflects the fact that the soils weren't ideal for crop production, because the bedrock, the limestone bedrock, is near the surface, and so it doesn't plow up very well and make nice soils for crop production. So we've got a bunch of grazing going on, and we can see it kind of coming together in this old picture from K-State campus. We've got some sheep grazing on the campus. And then this is Nichols Hall, and it's, like most of the buildings on the campus, it's made out of the limestone blocks that, the local bedrock, the reason why the shallow bedrock that is the reason why we don't have great soils for crops, except in some of the low-lying areas near streams. So the bedrock is Permian in age, right? So something like 250 to 300 million years ago. So what was happening during that time that created this situation? Well, this is a map that I think you guys have in that PDF, and it just shows this. This is the strip of where Permian bedrock is at the, is on the top of the pile, basically. Of course, there's soils on top of that, but when you're looking at the bedrock, this is what's on top, right, geologically. And you can see that it exists in western Kansas, but it's underneath the Cretaceous bedrock, right? So here it is. Here's the Permian bedrock, and it's outcropping right in this region of Kansas that we call the Flint Hills. So if we take a look at that bedrock, one of the things we can see is those chert nodules that give the Flint Hills their names. So chert, flint is just another name for chert. Some of these limes.
We have a question.
Sure.
Did you want to ask your question, Cam?
Why is there 100 million years of no sediment between the Permian and the Cretaceous period in Kansas?
Can you hear him?
I couldn't hear that.
Why is there 100 million years of no sediment between the Permian and the Cretaceous?
Yeah.
That's an excellent question. Sedimentary rocks are basically, it's like a book that can help us understand Earth's history. You just have to know how to read the pages. But one of the things about it is that most of the pages are missing. And this is an example of a big gap in the chapters, right? So what happens, we only get records of periods of time when there was depositional, when there was sediment being deposited. And most of the time that's going to be in a marine environment and in the oceans, right? That's where the sediment ends up ultimately getting transported and dropped off. So you have to have deposition, and then you also have to have those sediments being preserved, because later on that sediment can get uplifted and then it starts to get eroded away. And right here in Kansas, if we go back, let's go back a little bit. In Kansas during the Cretaceous, the whole state is not covered with sea, at least during this reconstruction. It kind of changed over time. Millions of years is a long, long time. But so like in this, if this is what existed, right? Eastern Kansas is not going to be a depositional environment. It's exposed on the land, and so it's not going to have a depositional record at that time, whereas Western Kansas would. So ultimately, it kind of comes back to those things. Is deposition happening, and then are those sediments preserved, or are they eroded away? And when we look at Kansas, I think the Cretaceous sediment was thinner. Anything that was deposited in eastern Kansas would have been thinner. And so if it was there to begin with, it was eroded away at some point. That's a great question.
Does that answer your question, Ken? Okay, I think he's good.
Okay. So we have these limestone beds. They can be, a couple of feet or less, even up to, maybe 5 or 6 feet in thickness. And they repeat over and over again, but mostly the sediments are these mudstones that can be kind of grayish, bluish, greenish color, all the way to kind of a reddish color. So you have these alternating cycles of mudstone, limestone, mudstone, limestone, and we can see this expressing itself in these kind of, we call it stair-step morphology on these on the hills in the Flint Hills. And this is a picture just from the Kansas floodplain down by the airport, looking south, so towards Konza. And you can just see that those ripples on those hillsides. It's just alternating layers of limestone and mudstone, limestone, mudstone, all throughout the Flint Hills. So why do we have that? Well, during the Permian, we also had a shallow inland sea here. And that shallow sea was kind of coming and going, coming and going. All right. And the reason, it was like a yo-yo effect, right? It's like sometimes the sea was there, sometimes it retracted, essentially. And the reason it was kind of going up and down like that, the sea level, was because during the Permian, there were glaciers at times in Antarctica. So Kansas was pretty darn close to the equator at that time during the Permian. So the tectonic plates have shifted quite a bit since 300 million years ago. So during that time, Kansas was pretty close to the equator. Antarctica was still down here, and there were periods of continental glaciation, and then periods of time that we refer to as interglacial periods, where the ice melted and that water went down into the ocean, and that caused sea level to rise. So sea level falls when the ice forms on the land, and then as that ice melts and flows back into the ocean, sea level rises again. Just goes up and down like that. Up and down. And this is right here a relatively shallow sea. And so that means that small differences in sea level can create, a big difference in the amount of area that's flooded with water. So here's a graph that shows sea level change since our most recent period of continental glaciation. So, that ended a little over 10,000, 14,000 years ago, something like that. Sea level rise since then is pretty substantial. So that's 120 meters right there. So you can see that the potential change in sea level just as a result of glaciation can be enormous. So that was causing this yo-yo effect. And in addition to that, as that's happening, climate is also changing. So the reason you're going from interglacial to glacial cycles is because of changes in Earth's climate over those periods of time. And it was this cyclic pattern of change. So when you change sea level and you change the climate, you're going to change what kinds of sediment are being deposited, if any, in a region like Kansas, where there was a shallow sea at times, versus soils. So limestone was deposited. I should say limestone formed from carbonate sediment that was deposited in a shallow sea. So when the water level was relatively high, and there weren't glaciers, it was an interglacial period in Antarctica. So the ice had melted. Sea level comes up, and then you start to deposit these carbonate sediments. And it was a pretty dry climate at that time. So when I say carbonate sediment, mostly what I'm talking about is like critters in the ocean make skeletons out of carbonate, like calcium carbonate, the mineral calcite, like clams, for example. And those materials can get broken up. To some extent, they're preserved, but that ends up creating a kind of like a lime mud. And, eventually if that gets buried and compacted, it can turn into limestone. So limestone formed when you had a shallow sea, arid conditions, and that's an interglacial period in Antarctica. So the ice is melted, sea level's high. And then as those glaciers started to form, sea levels falling, and the climate got wetter, and that caused more mud and sand to be kind of deposited in this like low area where there was the ocean. And you form these muddy, big muddy areas. Mud piles up, and you can form a mudstone eventually. If sea level keeps falling, eventually the mud would get exposed to air, and you would be able to form a soil. And these red areas that you see in the mudstones, those are soils. Those are ancient soils. And then this is going to be, like a mud flat or, near coast area where there was just a bunch of mud that was deposited. So we see changes in sea level associated with changes in climate that are affecting what kinds of sediment are being deposited here. Because there were times when we got these really nice limestones deposited, it means that we've got a bunch of limestone near the surface. It's also relevant that our climate today is relatively dry, right? So we're not forming a big thick soil here as well. And because of all of that coming together, this is an area where we have great grass and we graze cattle and other livestock instead of planting corn and growing soybeans and wheat, stuff like that. So geologically, there's an influence on how people are using the land here because it is affecting what soils look like. One thing I haven't talked about that I'm going to pull in a little bit more detail in the next example.
And I have a question from your previous slide, looking at the green layers versus the red layers, because it was my understanding that the red layers were red because of oxidation, because the presence of iron, and it was exposed to oxygen, so it oxidized, whereas the green layers were underwater and were not exposed to oxygen.
That's right.
Is that true? Okay.
Absolutely. Yeah. You see sometimes out west, you might be driving around, you see like really red colored rocks. Usually we call those terrestrial red beds. The place where you're going to form oxidized iron, like in that slide where I was talking about my research, that iron rust that was forming on that stream bank, you need to oxidize iron to form those oxide minerals like hematite and goethite. And so that oxygen is being generated by photosynthesis, so it's going to be up at the surface.
Right.
And if you're in a waterlogged mud, that oxygen, there's kind of a cap on that oxygen supply, right? Because it has to dissolve into the water, and then there's going to be bacteria that are respiring it and kind of keeping it.
But both of those layers are shales or mudstones.
So you could generally refer to all of this as mudstone, yeah, because
Okay.
it's mud and it's rock. So shale is a specific type of mudstone that's going to kind of break apart into sheets, not like a slate, but it's going to have like kind of a layering, and it's going to be formed from marine sediment specifically. So if you're not sure or whatever, I just call all of this stuff mudstone because I don't like to get into the
Gotcha.
specifics too much. I'm a lumper, not a splitter, if you want to put it in biology terms.
Right.
Yeah, mudstone's easier. Yep. Okay. So just kind of reiterate a little bit. We saw how changes in sea level in Antarctica were affecting the depositional environment here in Kansas, and ultimately that created these cyclic periods of time where mudstone and limestone and mudstone, limestone, so forth, were deposited and formed into rock, and because of that we have these shallow limestones. But part of the reason why we have not much soil on top of that is related to the climate as well. And we know that Kansas is relatively dry because we have this uplift in the Rockies. The Rocky Mountains create a kind of a rain shadow that affects Kansas. And I'm going to pull that in a little bit more here in this third example. But ultimately, it's all kind of connected together, right? And the point I'm trying to make is we're looking at some examples in isolation here, but it's all related to plate tectonics, and everything's it's a system of things working together. Okay, so in western Kansas, we're thinking about land use, since we've got a lot of cows and stuff around here, but out there, if you look at the landscape, there are cattle, of course, but there's quite a lot of agricultural crop production, and a big part of what makes that possible, allows us to sustain that through periods of drought, is the fact that we've got this really wonderful water resource, the High Plains Aquifer. And so in Kansas, there's three parts to the High Plains Aquifer. The Ogallala is the one you might maybe hear about the most. It's a geologic unit that makes up the most of the High Plains Aquifer. And then we also have the Great Bend Prairie Aquifer and the Aquifers Aquifer. And all together, these make up the High Plains Aquifer in Kansas. Now, I'll come back to that concept in a little bit, but this is all High Plains Aquifer. And so that helps, like I said, that helps us sustain agriculture. We haven't had, we've had droughts since the 30s, but we haven't had another dust bowl, right? It doesn't matter as much when the rain comes if you can just pump water up out of the ground and water your crops. So this is a huge win if you're interested in producing grain. It makes that land a lot more valuable. As many of you know, that Kansas is pretty dry in western Kansas, and it gets fairly wet in the east. This is this change in the amount of precipitation as you go across the state. The change in precipitation divided by the length of the state. That's the gradient that I'm talking about. And that precipitation gradient just across Kansas is bigger than the precipitation gradient across the whole eastern half of the country. This is a very steep precipitation gradient. And ultimately, the reason why this exists and the reason why we have those sediments that have have groundwater that form the High Plains Aquifer, ultimately those things come back to the laramide orogeny, which is the initial mountain building event that gave us the Rocky Mountains. And that happened, something like 70 to 80 million years to, 40-ish million years ago, depends on who you ask. But the main mountain building event happened during that time. And that's not to say that there isn't still uplift in the mountains. The mountains are still being uplifted a little bit in places. I don't know numbers, but anytime you're eroding the top of a mountain, there's going to be some upward movement of that mountain block. Imagine we can look at the reverse of that. If we had a boat in the river, we piled a bunch of stuff on that boat, the boat's going to sink down lower, right? You take stuff off the boat and it moves up. That's what's happening with the Rocky Mountains right now. They're moving up because climate is chewing away and eroding them. So, but in any case, the main mountain building event is referred to as the laramide orogeny. Orogeny is a geology term that just means mountain building event. So the laramide orogeny happened, like I said, during that time period, like 70 to 40-ish million years ago, something like that. During that time, you see there's still a subduction zone along the western coast, but you see it all along here. That trench right there, that dark blue line, that's a place that we refer to as a trench where you have a subduction zone. A subduction zone is when one plate of crust, of the Earth's crust, is diving beneath another. And there's kind of two broad categories of crust that make up the Earth's crust. One is oceanic crust and one is continental crust. The continental crust tends to be made up of rocks that make it less dense than the oceanic crust. And so as a result, the oceanic crust gets, when the two plates collide, the oceanic crust ends up going underneath. And it's that compression, these plates coming together, and this plate coming underneath and stuff kind of cooking off of that, that created the Rocky Mountains. So that's pretty cool, right? So I'm talking about some basic stuff related to plate tectonic theory. And the way to think about plate tectonic theory, I think my impression is that there's some folks that have some biology background in this crew. So I'll think of plate tectonic theory is to geology what evolution is to biology. So evolution is like the grand unifying theory of biology. It explains a lot of different phenomena. Same thing with plate tectonics. We can relate everything we've been talking about today. A lot of it we can relate to plate tectonics. Of course, there's also other stuff happening, changes in orbital cycles and things like that. But yeah, ultimately, one plate going underneath the other. There's volatiles that are cooking off that, creating melt and helping drive uplift. And then just the compression of the plates together causes some smushing effect that creates uplift and mountains.
Okay, so let's take a break. Does anyone have any questions? Yep, Kurt's got a question.
What is the rate of depletion of the overall aquifer, and how does that depletion impact the surrounding earth?
Could you hear him? Rate of depletion of the Ogallala Aquifer.
I actually have a slide in a little bit that looks at depletion. And, it depends on where you're at. We'll come back to this, but I'd say like in parts of Kansas, it's being depleted rapidly. And, we have a few decades left at the current rate. And then in parts of like central Kansas, south central Kansas, it's pretty stable. Did that answer the question?
I think he'll get to it.
How does the depletion of the underground water impact the soil that surrounds it?
So how does the depletion of the aquifer radiate to the above ground soils?
Or does it like collapse?
Or does it?
Well,
Does it affect the soil?
One thing that can happen is you can have land subsidence where you suck water out of the ground because the water is partially supporting the land. I haven't heard of much of that happening in Kansas. I think in general, you need more of a confined aquifer, and the High Plains aquifer is what we refer to as unconfined because it doesn't have big, thick, clay seam on top of it. So I don't think that's happening. There are examples of, streams going dry because they don't interact with the aquifer anymore because the water table has been lowered. And we're talking about a pretty big thickness of sediment on top of that. So the soil is quite a bit higher than the water table. So I'll talk a little bit more about those sediments. As I said, the western part is referred to as the Ogallala Aquifer. And then this is the Great Bend Prairie Aquifer. Here's Great Bend is right around here. And then Aquifers over here. And basically, these are just different geologic units that are hydrologically connected together. So when we think about an aquifer, we have to kind of separate ourselves from how we think about a geologic unit. So you might have some geologic formation, but you could have multiple formations that come together to form an aquifer if they're hydrologically connected. So we can think of it as a hydrostratigraphic unit or something like that. But the stuff in the west, the Ogallala, is older than this is Quaternary age stuff. So it's Pleistocene and Holocene deposits that make up the Aquifers and the Great Bend Prairie Aquifer. And then in addition to those units, you'll see alluvium listed here. Alluvium is stream deposits. And of course we have the Arkansas River flowing through this part of the state. And that's piled up a bunch of sediment. And that sediment is hydrologically connected to these older sediments that make up the aquifer. Now, I haven't pulled this back to what I was just talking about yet. So let me do that. Where do these sediments come from? Ultimately, we've uplifted the Rocky Mountains, and then there's just a bunch of sediment that's just being plucked away from that, and some of it's coming towards us. And so this, like the Ogallala started forming, the sediment started being deposited, I can't remember the exact dates, but sometime after the uplift of the Rocky Mountains. And then these came later, and some of this is just reworked Ogallala, and then some of it is new stuff that was also just kind of shed off of the Rocky Mountains. So the reason we have the sediments here, and I mentioned this earlier, the reason we have those sediments that make up this aquifer is from the uplift of the Rocky Mountains. And I just wanted to mention that, what defines something as an aquifer is not water quality. It's just the rock itself and whether the water can flow through it fast enough to supply a well. So what defines a well, depends on where you're at and how bad you need water. Or what defines an aquifer depends on how bad you need the water. But in general, the sediment that make up the Ogallala and the Great Bend Prairie and Equus beds, water can flow through there very easily. We refer to it as unconsolidated sediment because it hasn't been transformed into a rock. We call that process lithification. It's when you take a bunch of sediments, you smash them and cement the grains together. And when you do that, you can still make an aquifer out of that material, but it is going to seal up some of the pore space and the gaps between sediment grains and make it not as easy to flow water through there. But the Ogallala, Equus beds, and the Great Bend Prairie Aquifer, the water can flow through there very easily. This is a really beautiful aquifer. And in the thousands of years, actually, those sediments have been piling up for millions of years, but I think the water that's in there is thousands of years old. Water accumulated over a very long period of time, ultimately, is what I'm trying to get at. And so you have this beautiful sediment that water can flow through easily, and it had a nice big pool of water sitting in it. One other point before I move on, an aquifer is not an underground swimming pool, right? We can't take a dive in an aquifer. There are, exceptions if you had a cave system, for example, but usually it's like, water that exists in the pore space between minerals and rock grains. It's very small spaces. Okay, so groundwater depletion. So this is a recent report from the Kansas Geological Survey. And just looking at the numbers here, the colors tell us the estimated decrease in the percent of aquifer thickness. So how much of the original aquifer has been, depleted. And so the dark colors are the bad colors if you want to preserve the water and use it more sustainably. You can see that in places of western Kansas, there's quite a bit of depletion. Over 60% of the aquifer has been pumped away, and this is since we started, widespread use of this water resource, which was something like 80 years ago, and a lot of it within the last 50 or 60 years. But so the bottom line is we're taking water out of those places a lot faster than it's returning. And so the amount of water that's there is the amount of storage is declining. If we look over here in the Great Bend Prairie Aquifer and the Equus beds, actually it's pretty stable. And the water table is much closer to the surface. We've done a lot of work in this aquifer, and I think something like 10, 15 meters, the water is usually within 10 or 15 meters of the surface. And so the reason why it's more stable over here ultimately kind of comes back to the climate. Remember that precipitation gradient. It's much, it gets wetter pretty rapidly as you go east across Kansas. And so it's wetter here compared to here. And that means you don't have to pump as much water, and there's more water going in. So it's easier to sustainably use that water resource in these regions than it is here. So groundwater quality is the other thing. When you're talking about sustainability of a groundwater resource, it comes down to two things. The storage of water, how much water is there, quantity, and then also quality. And in western Kansas, where the water is being depleted, the water table is very deep below the surface. And it's probably, I suspect most of that is okay in terms of quality. It's not being affected by what we're doing at the surface. But in the Great Bend Prairie Aquifer, the water table is shallow. And the sediment that the aquifer is made up of, and above that, the soils, it's very sandy. So water that you spill on the surface goes down pretty quickly to the aquifer, to the water table. And we've been putting a lot of nitrogen fertilizer on those soils for the past, 40 or 50 years, several decades, let's say. And as a result, we're seeing pretty big increases in nitrate concentrations in the aquifer, particularly in shallow portions of the aquifer that underlie places where we're growing crops, which most of the area down there is being used for crop production. So this graph shows change in nitrate concentration. It's a box plot. So this is the median change over the last 40 years. We were able to compare data from 2016 from the 70s and 80s to make these calculations, to calculate the amount of change in nitrate. So the median change in shallow crop areas is about 10 milligrams per liter. Oh wait, is that right? It's pretty close to 10, I think. And 10 milligrams per liter as nitrogen, that's the maximum contaminant level for drinking water. If you're going to use this water for drinking water, it's not healthy to drink water that has more than that. It can interfere with the ability of blood to transport oxygen. There's blue baby syndrome. That's particularly hazardous for infants. It's not great for livestock. And in addition to that effect, there's also some other indications from epidemiology studies that suggest it might also be related to some forms of cancer and some other stuff. So ultimately, you don't want a bunch of nitrate in your water if you can avoid it. And some of the wells that we sampled saw really massive changes in the amount of nitrate. And we were able to demonstrate with isotopes that the nitrate was from fertilizer. So we know exactly what's causing it, and we need to do a little more work to figure out better ways to manage our nitrate in the agricultural activities. So water quality and water quantity are issues that are stemming from the way we use the land in western Kansas that are going to affect the quality or the availability and sustainability of that resource in the future. Okay, so these examples illustrate, how geology and climate and land use are all interwoven together. In the South, we saw how geology was affecting basically the composition of the rocks and ultimately the soils, and that affected how people use the land, and that affects the demographics of those populations there today, and how they, ultimately who they end up voting for and all of that good stuff. In Kansas, we see this strong aridity gradient across the state that reflects plate tectonics. And the geology that we see, the rocks that we have here, reflects those plate tectonics, as well as things happening 300 million years ago in Antarctica. And ultimately, these things affect how we use the land. We have grazing, substantial amount of grazing around here because of it, and we've got more crop production out west because we have that beautiful pile of sand that water can flow through really easily. And because of that aridity gradient, we really need it. So this goes way beyond humans. These things all connect to everything from microorganisms on up. One of the big projects that I'm involved in is in collaboration with mostly biologists and soil scientists. It's this NSF, National Science Foundation funded project. It's called MAPS, Microbiomes of Aquatic Habitats, Plants, and Soils. And we're looking across the Kansas aridity gradient at the microbiology of plants, the soils that those plants are in, and the adjacent stream habitats to understand how the microbes in those different systems, how they interact, how they're related, and how that ultimately affects things like water quality and soil quality. So geology is certainly a part of that. We need to constrain a lot of things about these systems to really put them in context and understand controls on those microbial populations. But we know that those microbial populations have a big influence on, the quality of our water, the land, soil, let's say soil health, greenhouse gas emissions from these environments, and climate, geology, and land use are major control knobs on those microbial populations. And then these interactions are changing with climate and as a result of unsustainable land use practices. So in terms of land use practices that are, we're going to have to make adjustments to looking ahead if we want to keep doing things that we're doing in Kansas. We're going to have to get a handle on water resources in Western Kansas. Might be that agriculture looks different one of these days because we can't pump water up when we need it. It doesn't mean you can't still grow stuff. It just means you're probably not going to grow corn. We need to do a better job managing our nutrients. We know that climate is changing and that precipitation gradient, it's getting drier. It's expected to get drier in Kansas. And so eastern Kansas might get a little bit drier, but we'll also see changes in the patterns of precipitation that are ultimately going to feed back on how we can use the land as well. Okay, and so with that, I think, we can open this up to talk about anything you want to talk about related to this talk or geology in general, but I thank you very much for your attention. And again,